Hi, y'all. I'm William Ntsoane, and I'm representing Kelson Marine at the International Partnering Forum in New Orleans. I know that not all of you could make it down to the conference in person, so I'm making this recording of what I'm about to share on the panel called The Original Offshore Farm, examining some supply chain commonalities between the fields of aquaculture and offshore wind. Hello everyone. I'm a mechanical engineer at Kelson Marine. We're out of Portland, Maine, and what I love about my job is diving into solving some of the ocean's most challenging problems. At Kelson, we're engineers who set out to minimize risk for farmers, developers, investors, and anyone who works in the ocean. Our mission is to bring advanced, model-based engineering to ensure viability for blue economy stakeholders by helping them reduce risks while lowering expenditures. We've helped partners deploy advanced ocean renewable energy and aquaculture technologies from New Zealand to Norway. This work leverages years of research and technology development funded by the US Department of Energy and other national and international agencies, as well as years of commercial projects. Our work covers everything from this project, developing a novel multi-body wave energy converter in partnership with GE, Marquette, and LPS, where the model predictive control is powered by a reinforcement learning algorithm, to aquaculture arrays that we've helped develop, de-risk, and deploy for cost-effective production in exposed sites, like this experimental composites-based array for seaweed cultivation that we tested in the Gulf of Maine. We also do sea keeping and optimization for autonomous surface vessels, heavy lift analyses, floating solar, all kinds of dynamic and exciting problems, challenges that we help solve in the blue economy. The engineering portion of the supply chain has a lot in common with that of offshore wind projects. Every ocean engineering project starts with identifying requirements in terms of survival, performance, spatial constraints, ease of operations, and economic metrics, etc. We rigorously quantify the mid-ocean data into a risk framework, then use validated physics-based models along with a large database of marine materials properties to evaluate the performance of the structure so that we can deliver detailed array designs and optimize existing designs for economic metrics such as capital or operational expenditures. Both aquaculture and wind are exhibiting steep increases in production capacity to meet a heightened demand both for food and for energy worldwide. Further maximizing production and harvest capacity will have the effect of making such products more cost competitive. Interestingly, this exponential growth in aquaculture closely matches that of the offshore wind industry. These industries will mature and grow together. So let's examine some of the commonalities in more detail, starting with CapEx cost profiles. According to NREL projections, 35% of the capital cost for a floating wind project is subsumed by substructure and foundation, as well as assembly and installation costs. According to some of our work with UMaine, vessels and anchor installation comprise approximately 26% of the cost of production for a large seaweed farm designed for co-location. Both industries must attain permits and social license, fund site selection and mid-ocean studies, and we must bear the costs of mooring and installation. Whether or not actual co-location is desirable or economical in a given situation, the overlap in the engineering supply chain between industries will help both aquaculture and wind projects get in the water. Both aquaculture and ocean renewables face significant challenges in obtaining regulatory and social license. So how do we address that? Of course, we work with ABS, DNV, and other marine standards to ensure safety for those who work on and around farms, as well as structural integrity. Proper array design, from spatial layout to material selection, ensures that these systems are designed not just to survive, but to perform optimally over their lifetimes, and can help address social concerns about navigability, viewscape impacts, ghost gear, and chances of marine mammal entanglements. Another critical step in the proper design of these arrays is rigorously quantifying the design conditions for any given site. In the ocean, we have lots of processes happening simultaneously, and to accurately quantify risks, it's crucial for both industries to understand the interplay between variables. There's been almost 100 years of research on extreme value analyses, but we're still finding new techniques to reduce uncertainty and simultaneously drive down risks and costs. For example, in a research project aimed at co-location, we took time series of measured wave height, period, and current velocity. Whereas we would traditionally extrapolate these values to their extreme values and then combine those 10 and 50-year values, we applied a contour-based approach to quantify the actual probability of various combinations of sea states, and found that the critical survival load cases specified by the standards were well outside of the actual 50-year contour seen here. Now, these interactions are complex, so how do we make all of this more accessible to stakeholders? The Kelson team has worked with the International Council for the Exploration of the Seas to take the complex interaction of currents, waves, and water depth that drive the forces on floating arrays and distill that into a single number we call the exposure index. We're still working on publishing this, and of all 6 candidate indices considered, our favorite is the specific exposure energy here, a measure of the energy per unit mass of water that combines both steady current and wave motions. We like this indicator because its energy is also proportional to the fluid drag on structures. We then use this new index to compare the exposure energy of, or to more so examine the exposure energy of sites in the German Bight of the North Sea, currently considered for co-locating seaweed and shellfish farming with wind parks. What we found was fascinating. So here we plot the 50-year specific exposure energy. It conveniently makes a scale that goes from about 0 to 10. Intuitively, behind the barrier islands, more sheltered sites are exposed to less hydrodynamic energy. But most interesting to us is how the sites with the highest exposure energy are those that are just off the coast, where large waves entering shallow water create large fluid particle velocities, and constrictions near the coast create strong tidal and storm-driven currents. So we need to decouple the term offshore aquaculture into separate metrics, the distance from shore and the actual exposure. Now let's look at how we can use all this precision in the engineering process to keep costs in check for mooring and foundations. Take, for example, this project funded by the Department of Energy, in which we were testing a novel aquaculture array with multi-line shared anchoring and composite lines. We started with wind, wave, and current data as per usual and translated the data into design load cases. So conventional risk management practice when sizing anchors is to calculate design loads based on these annualized load cases in combination with peak biomass. But we found that these conservative assumptions were costing the developer almost double the anchoring and installation costs unnecessarily. Essentially, we figured out that the worst storms and the highest biomass don't happen at the same time. And these cost savings, we were able to get an anchor that was really half that size. So just to show you some of the impact that this research can have. In another example, we teamed up with the University of Maine and the University of New Hampshire to evaluate the techno-economics of large-scale seaweed farming at offshore wind sites for marine carbon dioxide removal. We looked at over 60 different designs and operational inputs to optimize the levelized cost of carbon from this operation. Take, for example, the farm aspect ratio. As the aspect ratio increases, so does the amount of grow line available. That said, farms with greater aspect ratios also experience higher loads. So we see on the right that the capital expenditure costs for higher aspect ratios are higher, but when the cost is normalized by biomass produced, the highest aspect ratio actually leads to lower levelized costs. Now, how can you trust any of these numbers? Well, we don't just make models at Kelson, we do validate them. And due to the nonlinear character of hydrodynamics, we do all these comparisons against real-world measurements on full-scale systems in the ocean. Because of that, we have significant confidence in the answers we're providing to offshore renewables and aquaculture industries. So, at Kelson, we found that we can create value for both aquaculture and ocean renewable energy by using cutting-edge, model-based engineering techniques to develop and design and de-risk innovative technologies to create robust, economical design solutions to complex ocean engineering challenges. The industries of offshore wind and aquaculture have massive potential. The world's our oyster. These industries face similar challenges and have much to learn from one another. If you have questions on how certainty in a farm design, assurance for farmers and regulators, and investors, or realistic techno-economics can help humans use the oceans for good, we can go into more detail in the panel discussion. But please feel free to check out our website and follow us on LinkedIn, and I look forward to chatting with you all. Thank you.